Today we talk about hash tables. What is a hash table? Why do you use hash tables? Hash table is very powerful data structure. Is kind of strange because it's randomized, so it may cause you some problems in some strange situations, but it's widely used. So we'll discuss it, and we'll discuss what to do with hash tables and what not to do with hash tables and so on. So two major data structures based on hash tables are sets and maps. So what is a set? Set is basically self-explaining. So set is some set of objects, and you have functions like add objects to the set. Let's say add x, remove object from the set, and check that object is in the set. So it contains this. Very basic structure is widely used in various different situations. Like you want to calculate the number of unique objects in your list, you put them all in the set and then check the number of elements in the set and so on. Another data structure is map, of course. Map is basically like mapping from some objects to another objects. They call it key object and the value object. So it's mapping from keys to values. It's basically like an array, but as a key you use an object. So what are the basic operations with maps? Like you can insert new mapping in the map. Let's say put like in Java. And get the value by the key. Good enough. So these two are very primitive, very widely used in various different algorithms and various different real projects. Two very important data structures. Good. So how we implement the data structures using hash tables? Let's start with some simple case. The simplest case is when the key is a small integer number. So if key is a small, let's say, integer number from 0 to m-1, and m is just some small integer. How do you implement, for example, map if you want to have mapping from small integer to some object? This is called a dictionary in Python, for example. Yeah. It's the same data structure. Yeah. So, how to implement map or dictionary if the key object is just a small integer number? Basically what you can do is just to take an array and use this key as an index in your array. So you create an array, let's say array A of size m, and use your key as an index in this array. So for example, put just simply say index k equal to v, and when you need to get by index k, you simply return index k like this. That's all. That's the most simple. That's the most simple case how to implement a map when you have small keys. Now, what happens when the key is not a small integer? For example, if key is a big integer, let's say if key is an integer but from some big range for u, and u is big. What you can do? What you can do is to make some function which takes a big number and returns a small number, and use this small number as an index in your array. So we'll do the same approach, but instead of using key as an index, we will calculate some function from this key and use this function as a key in our array. So let's say we have function hash from k, and this will be a function from big range to u-1 to small range. Well, for example, let's say h of k equal to k modulo m. Cool. Nice function. And now how we implement these functions? I'll do it in the wrong way. We will fix it later. So what is the main idea? We'll do it something like that. kv, we'll say, we will calculate this function from the key and put the value v here. So now we change this index. Here the key is small, so we use this key as an index. And here the key is big, so we calculate this function, get a small number, and use this small number as an index in this array. Cool. And when we calculate get from k, we just return the same value. Well, let's have some example. For example, we have this array, say of size 5. And we make put, let's say, for some 37 value 3. So what will happen? We will calculate this function from this number. We will have 37 modulo 5, it's 2. Again? Okay. So it's 2. And we will put this value in the cell corresponding to this hash function. So 37 is 2, so we take this second element in our array and put this. Calculate hash from 37 equal to 2, and we use this as index in this array. And when we need to have get value from 37, we will calculate the same function, get the same value here. So we'll get the same index in the array. We will look in the same cell of the array and take the same value which we put here. So here, what is the idea? The hash function is always the same for this hash table. So here and here we calculate the same function. So we'll get the same result. So this index here and index here will be the same. So here we put this value in some cell of our array, and here we will look in the same cell, so we'll take the same value as we put here. Okay, that's basically the idea. That's the whole idea about hash tables. Now let's look what problems we'll have. Problem number 1. If you try, for example, get let's say 52. What will happen? You will calculate the same result, or the same function from this key. Calculate from 52. It will be 52 modulo 5, it will be again 2. So you will look in the same cell and get the result equal to 3. That's not correct. Yeah, this 3 corresponds to key 37, not to key 52. So you get wrong result because you just these two numbers have the same hash function. That's called a collision. So Collision is a situation when you have two different objects which have the same hash function. So objects x not equal to y, but they have same hash function. That sometimes happens. That's definitely happens because here you have many numbers. Here you have small number of items, and like if you have mapping from a big range to small range, you will have some collisions. Yes, by pigeonhole principle. Yeah. Okay. How will we fix this? First, let's fix our array. So we need some way to know which key corresponds to this value 3. So we can just put 3 here. We need to remember the key which corresponds to this value 3. So instead of putting this 3, we will put a pair of two numbers. We'll put here a pair, let's see, 37 and 3. So now our array contains pairs of numbers. Pair is a key and value. And here we will look in this cell, but see that this key is different. So here we have key 52. Here we have key 37. So we see that the key is different. So this value is not the value we're looking for. That's the whole idea. And the second idea. What happens if you want to put another value in the same cell of the array? So if you want here, for example, you want to put value, let's say again 52, key 52, value, let's say 5. So again, you want to have a map from integer to integer. So you need integer 37 to map to 3 and 52 map to 5. Yeah? But these two keys have the same hash value. So you look in the same cell of this array. So we somehow need to store these two values in the same cell. And the easiest way to handle this is just to make not in each cell of the array, make not one pair, but the list of pairs. So we'll just go in the same cell of the array and add this pair to the list of these pairs. So here we have one pair, so we'll put another pair here. And now this cell contains two pairs. Good. How we will implement this get operation? It's very simple. We calculate this hash function, go into this cell, look on this list, iterate through a whole list, and find the pair which corresponds to our key. Let's make a simple implementation. So when we put new pair into our hash map, we simply calculate this hash function, get this cell, and add pair key. So we just add this pair to the list of pairs in this cell. And when we make the get operation, we simply iterate for all pairs. Why I do it like this? I'm not sure what language is this, but so I try to iterate for all pairs in this cell and put these pairs as xy. And if x equal to k, then I have the pair which corresponds to this key. So I just return y. If I don't find the my key in this list, it means there is no key k in this list. It means that I should return null. This is very simplified implementation, because usually when you put the mapping for some key, if you already have this key in your hash map, you kind of want to remove it and put the new key back. Yeah. So if you already have this key k in your hash table, you kind of want to replace it. Let's just have a comment here. So this code is fine if this key is not yet in your hash table. So you just put this new pair and it's fine. If it may be in your hash table, you need to find this pair and replace the value. Something like that. Cool. That's all. Now let's talk about time complexity. That's complicated. Well, the time complexity of put is basically constant, because because again it is a simplified version. I don't look for this key. I just add a new pair in this list. What about this get? The worst case time complexity is definitely linear. And it actually may be linear. So what happens if you have some fixed hash function here? So if you have some fixed hash function like here, so if I just define this hash function is this. So you create a hash table, use this hash function, and think everything will be good. But in practice, if someone tries to break your program, and even if function is simple like this may happen just randomly, just because some data is not very random. So your data may be somewhat structurized. So sometimes it happens. You may have a lot of keys which have the same hash value. It happens. How to avoid it? Yeah, what? Yeah, you may try to use some more complicated hash function. Yeah, like this hash functions. It will not promise you anything. Again, if you use some fixed hash function, then someone may generate a lot of objects with the same hash value. It's always possible, because you have if this range is big and this range is small, there are a lot of objects with the same hash value. So someone could find a way to generate a lot of objects with the same hash value, and you will try to put all objects in the same cell of this array. So you have a list of objects in this cell. This actually happens if you look in the Java code. In Java, they have some fixed hash functions for standard objects. So if you have some strings, I don't know, longs, what other standard objects they have? If you look on the realization of hash code method in the standard Java objects, they use some fixed hash function. So it happens. You may have a situation where you have a lot of objects and you try to put them in the same cell in the array. That's a normal situation. Actually, in Java, they managed to use some different approach. They kind of use they use the binary search trees instead of lists to have this to have worst case logarithm time in this case. But not today. Today we're talking about different stuff. what I was talking about. How can you fight these situations like this? To fight this first, you want to use not some fixed hash function, but use some random hash function. Let's say for simplicity, let's say that hash function is just a random function from all possible functions from this to this. So we use all possible hash functions. What is the number of hash functions? We have m power u possible functions, right? So we have u values each from range of m. Yeah. So we have m power u possible functions, right? So let's say we just generate some function randomly from the whole set of all possible functions. Now, what happened? Let's see. What will be the expected time of time complexity of this get operation? Let's see. If we pick some key, calculate this hash function of k. What will be expected length of this list? So time of get, expected value of this time, will be equal to the size of this list. So what is the expected size of the list? Let's see. It is the expected number of elements which have hash function equal to k. Right? So this list contains all the keys in your hash map which have hash function equals to key. Okay. And what is this expected number? Well, let's see. For each element, the probability that not k. For each element, the probability that h of k equal to h of k, if they're not equal, yeah. So if x not equal to k, then probability that they have equal hash codes is 1 over n. Why it is so? Because the function is random. If we take absolute random function, this by symmetry, we have this probability equal to 1 over n. Is it clear enough? You can prove it more formally, but I think it's kind of intuitively. Yeah. Why is mu a function? Because what is random function? It's random function from this range to this range. So how to define a function? You need to define values h of 0, h of 1, h of 2, and so on, h of u, and all these elements are in range from 0 to m minus 1. Yeah. So there are m options for each value, and you have u values. So the total number of different functions is m power u. Cool. Now, if this probability is equal to 1 over m, then to calculate this expected value, we just need to have sum of all these probabilities, and so this will be equal to this. So it will be n multiplied by 1 over m. N over. That's the final probability. That's the expected that's the expected size of the list which we're looking for here. Okay. So if we have the size of array about n, then the expected time complexity will be constant. Okay. Summary for doing this. We're making hash tables. Everything I do is on the board right now. So I didn't erase anything by now. So that's the whole story by now. Cool. That was it. So again, if you take some random function and use this random function for your hash table, then the expected size of each list will be constant. So both these functions will work in constant time expected. Now, what if I don't like the collisions? So if you don't like the collisions and you want to avoid collisions, is it possible to have a big array? What I want to do? So, what if I don't like the collisions and I want to avoid the collisions? Is it possible to have an array of big array such that the probability of collision is less than epsilon? I want to have some big array and make it such big that the probability of the collision is less than some epsilon. Like this. Not sure what you're talking about. Can shift from 1 if the array is big enough. No, I want not to shift from 1. I want to shift to epsilon. I want the probability of collision be like small as possible. Like if you have, okay, basically it doesn't matter if this epsilon is less than 1. It's good enough. Yeah, you see. If this epsilon is 0.9, it will be enough for me. I will just run the same program 9 times, and I will get the array without collisions. But what should be the size of the array so that the probability of collision is less than some epsilon? Yeah, for some epsilon less than 1. And if you think about it, the problem is that if you want the probability of collision to be small, you need to have the array of size about n squared. The answer is that the size of the array should be about n squared. Why is this happening? No, basically because what's probability of collision? It is a probability that there are two elements with the same hash value. Yeah. And if you have n elements, Then you have n square pairs of elements. About n square. Like n square over 2, something like that. Doesn't matter. And each pair may have a collision with probability. So we have n square pairs. And they have collision with probability 1 over m. So to have this probability of having at least one collision be less than epsilon, you need this m. So you need this m be about n squared. That sometimes refers as Bose paradox. Yeah. Well, that's kind of strange. Mainly the idea is that if you have a group of, let's say, 30 people, then usually you have 2 people with the same birthday. They have like 365 days in the year, but usually 30 people is enough to have 2 people with the same birthday. Yeah, it's not n squared, it's n multiplied by n minus 1 divided by 2, something like that. It doesn't matter because we talk about asymptotics, so I just get rid of all constants. Cool. So why I was talking about this? That's the problem. You kind of cannot avoid the collisions without spending too much memory. If you want to avoid collisions completely, you need the array of size n square. And if you have million of elements in your hash table, you need kind of million square size of the array. Million square is too much. You don't want to have array of size million square. So for big values of n, you just cannot do it. But for small values of n, it's actually kind of valuable. Sometimes if you have small hash tables, you can do it like this. We'll talk about this in the next lecture. So sometimes you can do it, but usually if the size of the hash table is big, you're not allowed to spend this amount of memory. Cool. No. Cool. Now, this all was a good theory, but in practice, you cannot pick the random function from all possible functions. How can you do it in practice? You cannot do it in practice. Maybe you can do it in practice, but I don't know how. Because just to pick the random value, so just to save which value did you pick, you need some logarithm of this number of bits to store your hash function. So you have something like u log m bits, yeah, and you don't want to spend u log m bits because u is huge. Yeah? So this number u is huge, so you don't want to spend u log m bits. That's it. So all this theory was working when we have some completely random hash function. But in practice, you can't have completely random hash function. Yeah? Because number of function is too big. You can't pick random function. That's it. So what you do in practice? You do things like that. We will pick h not from the set of all possible functions, but just from small subset of functions. We will pick some small set of good functions, and each time we'll pick some random function from this set of functions. Let me see what I'm talking about. Let me show. So let's use only functions like this. Let's see, we have function from k equals something like that. Let's say we'll have k multiplied by some number a, then take it modulo p, and take it modulo m. And so this A and P are parameters of this function. And let's say P is a just big random number, big prime. No, it's random, that's prime. Zero is kind of strange, but good enough. Yeah, you may pick 0. It will be bad for a hash function. But that's fine. The probability that you will pick 0 is quite small. So let's use this set of hash functions. Again, where each hash function is defined by two integer numbers. First integer number is P, is some big prime number. And second function is A. It's just some random number from 0 to P minus 1. That's all. And now when we try to generate some random function, we just generate these two numbers. So we generate big prime number, we generate big number A. Why is it prime? I'll explain it a little bit later. I explain right now. And we use these numbers P and A as parameters of our function. That's all. Again, what happens? We try to have some random function, but we cannot take absolutely random function because there are too many functions. We cannot pick the random function from the whole set of functions. So we'll use only small subset of all possible functions. Only functions like this. And each time we'll pick some function from this small set. And now we'll see if it is enough to have the same time complexity in average. Let's go. Now, in parts like this, you kind of need to be careful. And to see what actual properties of your functions you need to have your proof of your time complexity. In this proof, the only property of the hash functions is this. So this is the only thing we used about our hash functions. Yeah. So this all these all are just simple transitions, and here we just use the some property of our hash function. This is the property of our function being random. Yeah. Electrical combination? No, it's not about combinatorics. The combinatorics is about discrete mathematics. It's only algorithms here. Yeah. We will not talk about combinatorics. That's not the topic of this course. So this is the property we need to make this proof. Let's see if this property is true for this set of random functions. Let's see. So what do we need? We need to calculate the probability that for two different keys for x not equal to y, probability should be about 1 over n. So if we prove this, we will use this fact here and have the same proof, so we have the same time complexity here. No, let's prove this. Yeah, let's prove. So let's see, put h of x, h of y, put it here, so we have x a modulo p modulo m equal to y a modulo p modulo m. Now I'll move this to the left, and since I have the same modulo here, I can just have this minus inside the brackets. So if I put this to the left and simplify this, I will get x minus y multiplied by a modulo P modulo M equal to 0. No, it's not. This modulo M guarantees you that the values are from 1 to n, but this probability may be bigger than n. This property is kind of that if you have two different keys, that they will put in different brackets or the different buckets of your hash table. Let's see. So why this is true? No, let's see what we have here. So here we have some number which is modulo M equal to 0. It means that this number x minus y a modulo P equal to some number which is divisible by M. So it's some k multiplied by M. Now let's see what number may be this. This is one of the possible ones. So it's M, 2M, 3M, and so on. And this number should be from 0 to P minus 1. So from 0 actually. From 0 to P minus 1. What is total number of numbers? How many numbers are in range from 0 to P minus 1 and are divisible by M? Basically, there are P over M possible numbers. Right. Here, from here to here. Here, what I say that this number modulo M equal to 0. Yeah? What does it mean? It means that this number is divisible by M. Right? Here just the same thing. So this number is divisible by M. I just rewrite it in a different way. Again, what is modulo M? It means that you have some number minus something multiplied by M. Yeah. If you have A modulo B, it's A minus K multiplied by B. So I just here I use minus K multiplied by M and then move it to the right. Sorry, I make two moves. So this thing should be equal to one of these P over M numbers, right? But if P is prime, you actually, there is a unique number which you can, so this number is not 0, because x and y are different. So for each number km, there is a unique number a, which gives you this product modulo P. So for each km, there is only one a that gives you x minus 1 a equal to km. That's basically because P is prime. You can divide by prime modulo. We'll talk about this in future semesters, just how to do it. Now it's not very important. Now what's important that, again, if you can I write it like this? So, for example, if P equal to, let's say, 7, yeah, and x minus y equal to 2, and so you have equation something like this. 2 multiplied by a equal to, let's say, 3 modulo M. Equations like this always have unique solution because this number is prime. Well, in this case, a equal to 4, right? So a equal to 4 is the only number which you can multiply by 2 and get the result equal to 3 modulo 5. It will be 8 modulo 5, it's 3, right? So for each number here, you have only one possible number a. So this equation holds if A is one of these P over M possible numbers. So you have kind of P over M bad numbers A. So let's say if this equation holds, it means we have a collision here. We have a collision here. So it means that A is one of these bad numbers. So we have this many bad values for A. And since A is random, what is probability that we pick one of the bad numbers? The probability that A is bad equal to P over M divided by total numbers of P. So it's over P. So it's 1 over. Actually, it's slightly bigger because here it's I need to have scaling of this. This +1. Yeah, doesn't matter. It's about slightly better, but it's not important. That's all. So we just proved that if we pick one of the random functions like this, then the probability of this will be about this. That's exactly what we need in this proof. That's all. And again, let's talk about this. You kind of need to be very careful when you work with hash functions, because sometimes you need different properties from your hash functions. For example, let me show you just a simple example. Sorry, I erased this. To A equal to 3 modulo 5, A equal to 3, yeah, A equal to 4, yeah, you have 2 multiplied by 4, it's 8, modulo 5, it's 3. Looks fine. What else? Let's imagine that we have some random hash functions, and this function, we have some different set of hash functions, and this set satisfies the following property. That's this property. Property that for each, the probability that hash function equals to I equal to 1 over M for all I from 0 to M minus 1. Just let's imagine we have some different set of hash functions, and we pick some random hash function, and we know that this property is satisfied. It looks kind of natural. What is this property? This property says that for each key, the probability that hash function equals to I equals to 1 over M. Yeah? So it's kind of, if you take one key, the probability that you put it in each bucket of your hash table is equal. Yeah? Looks kind of natural, right? So, is this property enough to have this time complexity? Now it's so, is this property enough to achieve the same time complexity? So if you pick some different set of functions, and again we will pick some random function from this set, and this set of functions will satisfy this property, is it enough to have the same time complexity here? You're thinking about this. This is just the simple numbers theory. That's not important for this lecture actually. It's just you're thinking too much about this. If you're not good about the numbers theory, you just watch another lectures about numbers theory. It's not that complicated actually. We use very primitive things. No, let's go back. Again, what I was talking about. If you have some set of hash functions, yeah, and you pick some random function from this set, and you prove that you have these properties, yeah, So for each key, the probability that you will put this key into each bucket is equal to 1 over m. So you kind of, for each number, it's kind of symmetrical. So you may put your element in each bucket with equal probability. Is it enough to have this time complexity or not? Let's have a vote. Is it enough or not? Just stop thinking about this. That's not that important. It's just some simple math actually. Okay. Again, we have one vote for yes. The answer is no actually. Why it is not enough? Because, for example, let's have a set of set functions like this. Let's have a function hi of x, which is equal to I. So, if you have a set of hash functions like this, and each time you just pick the random function from this set, yeah. So you may pick any function from this set with equal probability. So for each key x, the probability that this function will put you in this bucket is equal to 1 over m. But what is the problem? The problem is this function is the same for all keys. So you have this array A, and if you use one of these hash functions, it will try to put all your elements in the same bucket. So you have one big list and all will be empty. The probability of each list will be the same. So each list may be full with equal probability. So it's kind of symmetrical, but that doesn't give you anything. Because that's what you need. You need this property. And you always need to be careful about this. Because for different data structures, you may need different properties from your hash functions. In this data structure, all we need is this property. So it's satisfied here, so it's good enough. In different data structures, you may have some different properties. Sometimes pretty complicated properties actually. But here it's good enough. Okay. Do we have time? Oh, listen. Yeah. Oh no, I don't talk about this. I don't want to talk about some complicated data structures actually. No, I'm not ready to talk about this. Maybe next time. Now, what I want to talk. There are two more things I want to talk about. First thing is how to use hash tables when you have not integer values but some different values. If you use hash tables and your keys are not integers but some different objects, basically what you need is to make something like that. You want to have some set of hash functions which have some random parameters like this, and you use these hash functions these random parameters to calculate your hash functions, and you kind of want to prove something like that. We'll talk about this in home task next week. How to calculate different hash functions. What are actually hash functions looking in Java and Python and stuff like this. There was something else. Huh? Okay, let's move to next thing I want to talk about is a little bit different approach to handle the collisions. So here we have, again, collisions happens. You cannot avoid the collisions. If you want to avoid collisions, you need to have array of size n square. You cannot have an array of size n square. You kind of need to have some mechanism to deal with the collisions. There's one possible strategy. You can create a list in each bucket. You create a list of all possible keys in this bucket, and if you add one more key in this bucket, you just add it to the list, and so on. That's nice. It's working. The time complexity is good, so everything is good here. But there are different approaches, and now we'll talk about different approach. It's called open addressing. Addressing, is it right? I think that's correct term. Yeah. I'm not good with English terms. I think it's fine. Yeah. It looks like USB socket is broken at this pipe. That's no, I see. I have some. No, yeah, it's definitely something with USB socket. Okay, we'll fix it later. Now, I was talking about open addressing. Open addressing is another strategy to deal with collisions. What is the idea? Again, you have an array, and you put again. You do basically the same. You have this value. You calculate. Well, let's make it a little bit, because I have these pairs. So let's make this a little bit wider. So again, the idea is the same. You get this pair. You calculate the hash code. Put this pair in the cell. This hash code, so put it here. Again, you calculate this hash value equal to 2. Go here and put this value here. Now, you try to put some value in this cell again, 52 and 5. So again, you calculate the hash from this 52, go to the same cell and try to put this pair in the same cell. The algorithm is very simple. If you try to put some value in the cell, but the cell is occupied, you just go to the right to the next empty cell and put this pair in the closest empty cell to the right. So start from here, go to the right until you find the next empty cell, and then put this pair in this empty cell. That's all. That's the whole idea. let's write some simple implementation. So what happens when you put some value? Again, let's calculate the hash from this key and go to the right until we find the empty cell. Yeah. So while AI is not null, we just go to the right, and let's do it in cycles. So we say I equal to I plus 1 modulo n. Just make the cyclic array, right? So when you reach the right border, you just start from the beginning. So you find the nearest empty cell and just put your pair in this empty cell. Like this. Good enough. And how you make get? It's this key, this value. We're making map, yeah? So that's the key, that's the value. Okay. Now, how to make the get operation? What happens when you make get? Again, you make get of k. You calculate the hash value. Yeah? So you calculate the hash value of k. You find some position in your array. Now you try to find the pair which have key equal to k, starting from this position. So, where may be this pair with key equal to k? It's either here or to the right. So you go here and start to look for some pair which have the key equal to k. When do you stop your search? You stop your search when you reach some empty cell. So if you go to the right and then find some empty cell, it means that there is no k in your hash table. So if you start from here, go to the right. So these cells contain some pairs which is not k, and this cell is empty. Yes, they have the same hash value. So again, you try to put them in the same cell. So when you put the first one, you just occupy this cell. When you put the second one, you start from this position, go to the right until you find the next empty cell, and then you put this pair in the next empty cell. So you find the closest empty cell to your right. Yeah, hash map is simple an array. Is array with some tricks, let's say. Everything is arrays. So if you look in any data structure, you'll find some arrays, pointers, stuff like that. There's no some strange magic about data structures. They use some arrays, pointers, stuff like that. Everything is simple actually. Yes, and all arrays just store in the transistors and stuff like that. So computer is not full of magic; it's full of technology. So all technology is kind of, when you go to the bottom, it's something like that. So some basic primitive objects, and then you have some complicated algorithms on top of these basic structures. So you have some complicated structures. Tree is not an array. Everything is an array. Your memory is an array. You have random access memory. Random access memory is an array. Basically, you can ask it for value in some position, in some index of your RAM, and you will get the value in this position. So inside the computer, everything is basically an array. Not exactly, but very close to this. Now, what I was talking about. So here's the put operation, here's the get operation. How to make get operation? you want to get the value by your key. You calculate the hash of your key. Find this position in your array. Now you go to the right, trying to find the pair which contains the key k. There are two possible cases. If your key is actually in the hash table, then you will go to the right and eventually you will find the pair which contains your key. If key is not in your hash table, then you go to the right and eventually you will find some empty cell. If you find some empty cell, it means there is no key in your hash table. Because if there would be the k in your hash table, then again, if k is somewhere here, so we have this cell empty and k is here. This shouldn't happen because how did it end up here? When we put k in our hash table, we try to find the closest position to the right, closest empty position to the right. So the closest empty position to the right from here is this position. Why k is here? It shouldn't be here. Yeah. So if you go to the right and find the empty cell, it means there is no k in your hash table. Cool. So let's implement something like that. So we calculate hash function, and then again, why it's not null. We look in this cell I, see if first equal to k, then we will return so it means we will find the pair which have key k. If not, if we reach some empty cell, it means there is no key. We return null. That's basically the whole implementation of the open addressing hash map. Looks like this. Now, let's talk about time complexity and the size of the array. We need to store the pair of key and value, because when you make get, you don't know which key corresponds to this value. So if you have different keys with the same hash value, you go to the same cell and you don't know this value corresponds to this key or this key. So you kind of need these pairs if you need to have map. And if you have collisions, and if you don't have collisions, you actually don't need this. If you have collisions, you need some way to distinguish different keys. Now, so if you have hash table of n elements, what should be the size of the array? Well, let's say if we have the size of the array equal to n, what will happen? Some strange things will happen. Now, think about it a little. You have an array of size n. You put n values in this array, so all cells are occupied. No? What trick? What trick? What trick? What trick are you talking about? Let's look here. Here we have array of size 5. What will happen if you put 5 values in this array? No, simple thing will happen. All cells will be occupied. Yeah. So you put this. If you make another 3 puts, put something, and put something in this array, then all cells will be filled with some element, right? So you have no empty elements of your array. Now, what will this file do if all cells are occupied? It will work infinitely, because you start with some cell and you try to find the closest empty cell, and you can't find this empty cell. So if you call this get operation with some key which is not in your hash table, then this while will work infinitely. So your program just hangs up. How to fix this? Now, you fix this very simple. You make array not of size n but of size 2n. Actually, I think 1.5 should be enough. Not sure about this. I will not talk about this. 2n is, yeah, 2n I am pretty sure is enough to have a quite good hash table. So what happens if you have m equal to n? It means that about half of your cells of your array are empty. So you have something like this. So you have the array size 10 and some 5 elements are occupied. So something like that. So there are many empty cells in your array. And if you start at some position, you go right to the closest empty cell. Closest empty cells will be quite close, because there are a lot of empty cells in your array. Again, let's do this. Let's do this. It's circular here. Yeah, it's circular here, and it's circular. Here I didn't move the I. Yeah. And you didn't know this. Yeah. Again, time complexity depends on number of steps of this while, right? And this while. So number of steps of these whiles depends on the distance to the closest empty cell to the right. So you start in some position. I have the same pictures there. Huh? Okay. And try to find the closest empty cell to the right. And the time complexity depends on the number of steps you need to make to find the empty cell. Well, let's think. If all empty cells are somehow randomly distributed, so if you have some random function, it's almost true. These empty cells are evenly distributed because among all the cells of the array. So each cell may be empty with probability like a half. Yeah? Probability that AI equal to null equal to 1/2. Yeah, because half of cells are filled, half of cells are empty. So here you continue your while if the cell is not null. So the probability that you will go on the next step of your loop is 1/2. So what is, if we say that that's true, it's almost true. What will be the expected number of steps until you find the empty cell? It will be so if you make each next step of probability 1/2, then the number of steps will be 1, right? So expected number of steps will be 1, right? Which is 1 step of probability 1/2 plus 2 steps of probability 1/4 plus 3 steps probability 1/8 plus and so on equal to 1, right? No? No, that's not true. Because shifted, it means it's zero. That it's 0 steps probability 1 over 2. Yeah. And 1 step. Like this. You can think about it a little bit different. So, what is the expected number? So, we make the first step with probability 1 over 2. We make the second step with probability 1 over 4. First step is 1 over 8 and so on. So it's 1. That's definitely 1. Now, that's almost true, not exactly. What is the problem? That these probabilities are not independent. So, because of the way how do you put these elements in your array, there may be some clusters of field cells. What happens when you use open addressing hash map is like this. If you have some series of occupied cells, some big cluster of occupied cells, there is a big probability that the next element you will put in your hash table will be put in this cluster. So you try to put the next element and you go into here. And if your hash function is inside this cluster, then you will put your value in the next element right here. And you will extend this cluster even more. So what happens in open addressing hash maps is that these clusters have tendency to grow. If you have some big cluster of occupied cells, then with big probability it will be expanded even more. This may happen. This happens sometimes. That's fine. The probability of this is if you calculate the probability good enough, I believe for m equal to n, the expected time complexity of get is still constant. I'm pretty sure it is. I didn't check. I didn't check. No, it must be constant. I don't know how to prove this exactly, because that's not that trivial to prove. That's not trivial to prove because of this clustering stuff and so on. But I'm pretty sure it's still constant. It's not that important for this lecture, but you may try to find the correct proof. What's good about open addressing? Let's talk about what is good about open addressing, why I love open addressing, why it's used sometimes. It looks like it's kind of overcomplicated stuff, right? So why do you use open addressing when you can use just simple lists? And we proved that the time complexity is good. There is no magic like this, no clustering, no stuff like this. The good thing about open addressing is about it's quite efficient. You don't need to have these lists. Lists actually uses some memory you need some additional memory to store these lists. And if you use, for example, linked list, you need to have additional pointers to each element. Like how do you store linked list? You have a pointer to the next element. So for each element, you need to have an additional pointer to the next element. And also it's not good for caching. If you have linked list, then when you iterate over linked list, you need to jump over the memory in random order, and it's not good for caching. And if you use open addressing, it's very good for caching because you iterate some continuous segment of your array, and your memory works works in that way. So if you have some continuous access to your memory, it's very fast because the caching works pretty fast. if you load one element of your array, the cache will lose the block of elements. We will talk about this in the future lecture. So in practice, this may be more efficient than the approach with lists we discussed before. So it's kind of cool stuff for practice. What if when hash table is empty? No problem, we go here, it is null, so we jump here, return null. Now, if hash table is empty, then all cells are null. So we go here, see it is null, go here, return null. No problem. Final. What can you do with this problem? How can you avoid situations like this? There are several approaches which help you to avoid clustering like this. Basic approach is here. What we did here, when we find this cell is empty, we go to the right with step equal to 1. So each time we step one cell forward to the right. You can, that's not exactly, not what you do. You can do it in a different way. For example, you can make each next step bigger than previous step. You can make step 1, then make step 2 cells to the right, then make 3 cells to the right, and so on. So if you start here and you find this block, you first go 1 cell to the right, then 2 cells, and you go to the same cell. Yeah. Let's have more occupied cells. So first you move 1 cell to the right, then 2 cells to the right, and 3 cells to the right. 1, 2, 3. And put your value here. That will somehow decrease the size of these clusters. Also, you can do it even more. You can make each next step equal to. So if you make step on step I, you make jump on I square. So you make first jump of 1 cell to the right, then 4 cells to the right. 4, 2. When you jump here, then you jump 9 cells. So first jump 1, then jump 2, then jump 9, 4, and so on. So here, it's there. So here we only jump 1 cell to the right. You can change this. You can make a jump of different length as soon as you have the same jumps for the same value k. So for same value k, you need to make the same jumps here and here. So here and here, you need to make the same jumps. Yeah? Because when you put the value and when you get the value, you need to visit the same cells. Yeah, that's it. Yeah, finally, what you can do is to make jumps, make the length of your jump also random. You may have jumps of size so you start from here and make jumps of some length. You make this length equal to another hash function, so hash 2 of k. So calculate 2 hash functions. First hash functions you use to find the initial index in the array, and second hash function you use to make these jumps. And again, this second hash function will be the same here and here. So you will visit the same cells in both these functions. It means if you put something in the hash table, you will find it in the same place. That's it. Okay, but caching is not as good here. So it's here. If this hash function is big, then you have problems with cache. You have a lot of cache misses. Basically, every time you go, you have a cache miss. So it's kind of trade-off between this and this. Now, final few thoughts about hash tables. First, again, how do you implement hash table? You pick a hash function from some set of random functions. You pick a random function from some set of functions and use this as your hash function. Now you create all these algorithms and so on. And if your function is actually random, then actually everything is good. But what may happen? If you choose some random function from your set. Starting from this point, everything is not random. So the only random point is when you pick your hash function. After this, everything is determined. So everything after this point is not random. So what may happen? It may happen that you pick some random function and create your hash table. And then somebody find out what hash function do you use. Somehow, I don't know. And he start to gives you the values which have the same hash function. So again, if someone knows what hash function do you use, he may give you a lot of keys with the same hash function. What can you do? So imagine you have some hash function. So you have this value. And someone gives you some operation. You put some k1, put k2, put k3, and so on. And they all have the same value of h. How can you avoid situations like this? First, how can you detect a situation like this? Well, it's very simple. You can detect this. So if some bucket is too big, so if you check the sizes of buckets in each cell of your array. If one bucket is too big, it means that something is going wrong. So we just proved that the expected size of bucket should be constant. So if one bucket looks too big, it means that something is wrong. We kind of make this check, like each, let's say, 1,000 operations, that some bucket is too big, it shouldn't be that big. And if one bucket is too big, what you can do is to get another random function from your set. So again, you look to your set of random functions, pick another random function, then throw away your previous hash function, use the next hash function, and recreate the whole hash table from scratch. So again, you get all elements from your hash table, create another hash table, and put your elements in the new hash table with the new hash function. And if all these keys have the same hash function here, for the new hash function, it will again be random. Because we take the new hash function, so they all have different hash values. So again, all this probability stuff works. So yeah, if you find out that something is strange, you may pick another hash function and rehash everything. That's one of the way to deal with this. I'm not sure about properties of these functions. That must be a complicated proof. I think there is no easy proof for this. I'll check. I never tried to prove this actually. I'm not sure which properties do you need to have this. Not sure about this. That's all. So again, what you have, if you see something wrong, you may throw away your hash function, pick a new hash function, and rehash everything. Creating the hash table from given elements works in linear time, because if you in expected linear time. So if you make it from time to time, it's okay. So if every n operations you rehash everything, you spend another n operations. So again, the amortized time will be constant. And in the same way, what happens when you imagine you have this, what usually happens? You have some hash table, yeah, and you like put a new values in your hash table, and you actually don't make this array of fixed size. Yeah? If from the beginning you know that you will put like n elements in your hash table, you can create an array of size n, yeah, and put n elements in this array. But in practice, you usually don't know how many elements will be in this array. So you create some array and try to put these elements. What happens when you have too many elements in your hash table? Like in vector, you throw away your current hash table, create a new array twice bigger than the previous array, and put all your elements from previous hash table to the new hash table. Again, it works in linear time. And if you make it when you increase the size twice, the amortized time will be constant, like in vector. You need a generator of, yes, you kind of need some way to generate a new random function. Yeah. Again, we in the random function we discussed, we have only two random parameters, so you kind of need to generate these two numbers. Yeah, you may create another function which gives you a new hash function. That's a nice approach. Why should we use binary search tree? That's a nice question. We will talk about binary search trees in the next semester. It is another data structure used for maps and sets. Two possible ways. There are two things why it may be better than use hash tables. First thing, of course, because it is not randomized. The time complexity of binary search tree will be always log n. In worst case, there is no magic in balanced search trees. It's very simple, very robust data structure. And the second, why will we use binary search trees? Because there are many more operations in binary search trees and hash tables. Basically, binary search tree allows you to have some sorted list. Here we have some set of elements, and then binaries we have them in some linear ordering. So we can go to the next element, to the previous element, find maximum, minimum, and so on. So we'll discuss all this in the next semester. Binary search trees looks kind of the same because they're used for maps and sets, but they also allow you a lot of different operations which are not maybe implemented in hash sets. So hash sets just give you a set and a map. So you can have the set of elements and check that element is in your set, or you have a map and get the value by the key. That's basically all you can do about hash tables. And in binary search trees, you can have the order of elements. So you can find previous elements, next elements, and so on.